Hello and welcome. If you're a physics student, you've probably heard whispers of the infamous Irodov problem book. Well, today we're diving headfirst into one of its classics. We're going to break down problem 1187, which is a fantastic puzzle all about a collision and this tricky thing called angular momentum. So, you ready? Let's get started and see what makes this problem tick. But hang on, before we start plugging in numbers, let's just think for a second. We all get momentum in a straight line, right? But what happens when things rotate or even just fly past a point? What makes momentum angular anyway? And what are the magic rules that decide when it stays the same versus when it changes? Keep those questions simmering in the back of your mind. So here's our scenario, straight from the book. We've got a disk, mass m, just sliding along with velocity v. It's about to smack into a smooth wall. Now, the problem gives us two huge clues. The collision is perfectly elastic, and the wall is smooth. We also know the angle it hits at, which is alpha. Our entire job is to figure out what happens to its angular momentum. Okay, that's the setup. Now what's our game plan?
Simple. Here's our roadmap for today. First, we'll dissect the setup of the collision puzzle. Then we'll open up our physics toolkit and look at the laws we'll need. After that, we'll solve part A, then part B, step by step, and we'll finish up with the key takeaways you can use for other problems just like this one.
All right, let's get into it. You know, with any physics problem, if you don't fully understand the setup, you're just setting yourself up for failure. So let's make absolutely sure we're all on the same page here.
Let's look at the ingredients. We've got our disk with its mass and velocity. Now, when the problem says the surfaces are smooth, that's just physics code for ignore friction, which makes our lives way easier. Then there's perfectly elastic. That's another huge clue. It basically means it's a perfect bounce. No energy is lost. And finally, the angle, alpha. So with all that info, our mission is to track the disk's rotational momentum, its angular momentum, through this whole event.
Okay, to solve this thing, we can't just throw random equations at it. We need the right tools for the job. So let's pop open our physics toolkit and make sure we're fresh on the fundamental laws that are going to govern this whole thing. First up, good old linear momentum. You've seen this a million times. It's just mass times velocity. Think of it as the oomph an object has when it's moving in a straight line. But the most important thing to remember, and where a lot of people trip up, is that it's a vector. Direction matters just as much as magnitude. Now for the main event. Angular momentum is kind of the rotational version of linear momentum. But here is the big mind-bending idea. Its value isn't just a property of the object itself. It actually depends on where you choose to measure it from. It's all relative to a point you pick. See the formula? M equals r cross p? That r is the position vector from your chosen origin to the object. If you change your origin point, the angular momentum of the exact same moving object changes. This idea is absolutely crucial for this problem. So if angular momentum can change, what causes it to change? Well, the answer is torque. It's a really nice analogy. If a force is a push or pull that changes linear momentum, a torque is a twist that changes angular momentum. And look at that formula, it's so similar. Torque equals the position vector r cross the force F. And honestly, this table just lays it all out perfectly. You can see these beautiful parallels between linear and angular motion. Linear momentum has an angular counterpart. Force has torque. And here's the kicker, the most important line for us, the conservation law. For linear motion, if the net force is zero, momentum is constant. And for angular motion, if the net torque is zero, angular momentum is constant. That last bit is the entire key to solving part A. Okay, we've got our tools ready. Let's start solving. Part A asks, relative to which points does the disk's angular momentum stay constant during this collision? So we're basically hunting for spots where there's zero net torque. Let's just reason this out together. If we want the angular momentum m to be constant, what does that mean about its rate of change? Well, it has to be zero, right? And what did we just say causes angular momentum to change? Torque. So the logic is really straightforward. For m to be constant, the net torque must be zero. Our job now is to find all the points in space where that condition is true. Okay, let's walk through this. Step 1, what's the only force we care about during the tiny moment of impact? It's the normal force F from the wall pushing straight out. Step 2, we know the torque formula is r cross F. Now for the big insight in step 3, how do we make a cross product equal to 0? Well, the math tells us it happens when the two vectors, r and f, are parallel to each other, when they lie on the exact same line. So that leads us straight to our conclusion in step 4. If we pick any point on the line of the force F, our position vector r will be parallel to F. The torque will be 0, and bingo, the angular momentum about that point is conserved. Nice. Part A is done. Now for part B. This time, we have to actually calculate the change in angular momentum. And we're measuring it from a point O prime, which is some distance L away. Now, since this point is not on that magic line of force we just found, we should expect a non-zero torque, which means the angular momentum is definitely going to change. Pro tip for any collision problem that happens at an angle, the first thing you should always do is break your velocity vector into components. Since the wall only pushes perpendicularly, it makes a ton of sense to split the velocity into a part parallel to the wall and a part perpendicular to it. A little trick gives us v sine alpha for the parallel part and v cosine alpha for the perpendicular part that's heading right into the wall.
So what do those keywords, perfectly elastic and smooth wall, tell us about what happens to these components? Well, smooth means no friction, so there's no force along the wall. That means the parallel part of the velocity, v sine alpha, just cruises on by, completely unchanged. And perfectly elastic, that means the perpendicular part, v cosine alpha, just bounces off perfectly, reversing its direction but keeping the same speed. That's it.
So, to find the change in angular momentum, we first have to find the change in linear momentum. And the tool for that job is the impulse momentum theorem. It's a really powerful idea that just says the change in an object's momentum, delta p, is exactly equal to the impulse it receives from the net force. Let's calculate that change. The parallel momentum didn't change at all, so that's a big 0. All the action is in the perpendicular direction. The momentum goes from mv cos alpha into the wall to negative mv cos alpha away from the wall. The total change is always final minus initial, so that's negative mv cos alpha minus mv cos alpha. The result is a total change with a magnitude of 2 mv cosine alpha. That's the total impulse the wall gave the disk. Now, hold on. Here's a classic trap, a little bit of ambiguity that you see in tough problems like these. The problem tells us the distance L, but it doesn't say in which direction point O prime is. To actually solve this, we have to make a reasonable assumption. The most logical one is that O prime is in the plane of the disk's motion, along the wall, and it's always good practice to state your assumptions out loud. And now we can put it all together. The change in angular momentum, delta m, is r cross delta p. In our case, the position vector r has a length L and is parallel to the wall, while the change in momentum, delta p, is perpendicular to the wall. That means they're at a perfect 90-degree angle to each other, and when that happens, the math for the cross product gets super easy. It's just the magnitude of one times the magnitude of the other, so we just multiply L by the delta p we just found, and there it is. The final answer is 2 times mvl cosine alpha. And there we have it, problem solved. But you know, getting the answer is only half the battle. The real win is understanding the powerful physics concepts we use to get there. So let's quickly recap what we really learned today. First, and this is a big one, angular momentum is all about perspective. It completely depends on the reference point you choose. Second, torque is what makes it change. No torque, no change. That leads to the third point. Conservation of angular momentum is your best friend when the net torque is 0. And finally, a practical skill, breaking vectors into components is an absolutely essential strategy for solving collision problems. So that's a wrap. But I want to leave you with one final thought to chew on. Our whole solution hinged on the collision being perfectly elastic. What if it was inelastic? You know, kind of a mushy collision where the disk loses some energy and doesn't bounce back with the same speed? How would that change our delta P? And what would that do to our final answer for delta M? Thinking that through is a great way to really make sure you've got this down. Thanks for joining me.